I'm Marcus.
And I'm Daniel.
This is our 2022 Base F Science Fair project.
And it's called the Smart Watering System. Abstract. We built a system using Raspberry Pi that waters plants based on detecting when the soil is dry. We then made some major improvements which we will also explain in the slides coming up.
Lettuce is Canada's biggest vegetable import. It has shallow roots, so frequent watering is better than deep watering. An automatic watering system would work better for lettuce than people who aren't available to watch and water their plants.
Purpose. Our purpose is to simplify the job of watering plants indoors. This would help fellow Canadians grow their own vegetables in their homes, even in the winter. Some of the benefits would be to reduce vegetable imports, transportation fuel usage, global warming, pesticides, and preservatives.
The materials on the left are all related to Raspberry Pi, like sensors.
And the materials on the right are all related to growing the plants, and some of them include like a reservoir. We'll be explaining more of these in the next slides. Hypothesis. We hypothesize that we can build a system that will automatically water a plant when it is dry, at any time of day or night.
Raspberry Pi connected to the soil moisture sensor and reading its signal wet or dry. The Raspberry Pi is basically a computer with an operating system. It connects to a keyboard, mouse, and monitor. It is unique because of its GPIO pins, which can be used to connect wires to external equipment like sensors, pumps, monitors, and many more. Moisture sensors can be used to detect soil wetness in plants. They can send a signal to a Raspberry Pi to tell if it is reading wet or dry. There is a certain point where it will flip between wet and dry, shown by the dotted line in this picture. We connected the sensor to the Raspberry Pi through the breadboard. The red and black wires are for power, and the green wire is for dry or wet signal. We used Python programming to receive and store the sensor readings and display them on our monitor.
Version 2. Adding the pump in the water reservoir to water the plant. The pump has an inlet hole at the side to suck the water in and an outlet hole at the top to push the water out through a tube that will be connected. We could only find 5-volt pumps to buy. We have a problem because the Raspberry Pi GPIO control pins only output 3.3 volts. We learned that a relay device can solve our problem. Relays can be controlled by Raspberry Pi to turn a switch inside the relay on or off. This switch can turn on another circuit on or off on the other side of the relay, which needs its own external power supply. We connected the Raspberry Pi to the relay to power it, and also to control its switch. We connected the pump and the 5-volt power supply on the other side of the relay. The pump was placed at the bottom of the reservoir. We added code to our Python program to turn the pump on whenever the soil is dry. We tested how much water the pump could deliver in different heights of the tube apex and different lengths of time using a measuring cup as shown in this diagram below. We noticed that the average between low, medium, and high heights differs by about 5 milliliters per second.
Version 3. Protecting the pump with a second soil moisture sensor. We realized that when there is no water left in the reservoir, the pump would struggle and burn out if it runs dry for a long time. To fix this, we positioned a second sensor so the detection point is above the pump, like shown by the dotted line in the diagram. The tips of the two prongs are 1 inch off of the bottom reservoir. We connected the new sensor to the Raspberry Pi like we did for the first sensor, and programmed it so that it detects dry. It will pause any pump actions until the reservoir is filled again.
Version 4. Send email when reservoir is empty and when plant is watered. The pump is now protected, but the plant might die if the owner doesn't notice when the reservoir is dry. To solve this, we coded a way to send an email to the owner from our Python program whenever the reservoir is empty so they could refill it. Above is a screenshot example of one of them. We sent over 60 during our testing.
Version 5. Setting up a database to track system events. We noticed that with so many emails, it wasn't easy to see how well the system is operating over many days or weeks. So we programmed a Maria database to store import events in a table. This table shows the 3 columns we set up. and some example rows from our system.
This is our setup. So you can see it here as well, but it might be more clear on the screen. So the Raspberry Pi supplies power through the breadboard to the sensors and the relay. And whenever the sensor here detects that it's dry, the relay will turn on and push water from the pump, the reservoir to the plant. And this is a demonstration of it working. So in this video we started with the dry plant, just for demonstration. And this is going through all the equipment like was showed in the last slide. And now we're going to click run. So it detects the plant is dry, as you can see, and it'll turn on the pump. And after turning on the pump, it'll detect that the plant is wet. And now it'll wait for the next time that the plant is dry, and everything goes as it should.
Conclusion. We were able to accomplish our hypothesis by building a system that waters a plant when it's dry. We originally wanted to use our system to experiment on lettuce plants, but it took way longer than we expected to grow from the seeds. So we made the following improvements in the meantime. Use a second moisture sensor to protect the pump from burning out. Alert the plant owner with emails when the reservoir is empty and the plant is watered. Store important events in the database so they could be analyzed to make future upgrades. We believe our system could be useful in Canada and other parts of the world, especially in colder climates. It could be used in homes or expanded to greenhouses and give the following benefits. Stop the use of pesticides and preservatives, making the food healthier and tastier. Dramatically cut down the amount of transportation, emissions, and global warming. We have learned tons about Raspberry Pi, Python, circuits, sensors, pumps, and relays during this project. This project was a lot of fun. If we had more time, we would send emails giving an estimate of when the reservoir is expected to need refilling, use our system to experiment on lettuce plants, and then add LED lights, etc.
We would like to thank our parents for providing us with the materials and coachings with the Raspberry Pi, and both of our grandparents for inspiring us with the growing vegetables at home. Thank you.